We mentioned in section 4.3 that energy conservation is one of the key components of good BRDF. Unfortunately, our current BRDF using the Cook-Torrance model is not exactly energy conservative. Lambertian diffuse BRDF does not account for the light that reflects at the surface. And that is therefore not able to participate in the diffuse scattering event. I'm not understanding that.
I'm not sure what they're trying to say there.
Okay.
Is that like it's basically saying that like because we've separated out diffuse and specular, we're not necessarily properly removing the light that went into the specular reflection?
Oh yeah, I think you're right. Yeah, because Lambertian is just equal chance to go in any direction.
Yeah, it does have the FRFD thing right there that you're highlighting.
The way that I understand it is since a Lambertian like diffuse surface is perfectly smooth as a diffuse surface, it cannot like it's not able to scatter against like other like microfacets and whatnot. That's how you get like retroreflection and whatnot.
Well, the surface isn't smooth; it just reflects smoothly, right? Like it's
yeah.
It doesn't have a compensation term for like if you have light that's reflected by a specular BRDF in addition to the Lambertian. Like maybe it's kind of somewhere around that.
Yeah, like the surface has still got the whole microfacet like roughness, and that's what kind of gets the light to be like absorbed, right, and then reflected elsewhere because it's reflecting around. But so it's more like, isn't it like at every angle coming out of the surface, it's got the same amount of light, but the surface still doesn't mean it's smooth.
Yeah, I think that is relevant to do to add a little bit more discussion.
Yeah, I really want to know more about that.
Yeah, but they have to do so.
Yeah.
This explanation has been left as an exercise to the reader.
Energy loss in specular reflection. For a single bounce of light, because it models the shadow by just one parameters. And it's only account for one bounce. I think that's why. This can cause a loss of energy at high roughness.
So this is because of the choice of like distributions we used?
Not distribution, it's with the it's a geometric shadowing this term.
Yeah, I think I kind of intuitively get what they mean, because I mean, just with the illustration, like if you're only doing one bounce, you can't really account for like multiple bounces there. Or if you only
And I don't think you'll be able to see that in the equations very easily.
Yeah, like I was like, I'm curious where the single bounce comes in? Like, is that in the choice of like that like distribution they use only models the results of a single bounce?
I think so.
But yeah, I think the BRD
Yeah.
is kind of just the one bounce. Yeah.
Because the BRDF is constructed by saying, okay, we have a surface that is subdivided into a bunch of flat surfaces that are all at different angles to each other. And then they just kind of do the integral and figure out how to, well, not do the integral, but they come up with an approximation for that idealized surface for that. And when you only account for a single bounce, it has the a much simpler form, I would say.
Right. Okay. Yeah. So like Leslie, you're saying that's in the G term, the geometric
Yeah.
shadowing. So I guess that fancy equation would be, yeah, you'd need to have less fall off if you wanted to take into account multi scattering, because it would be able to escape being shadowed easier.
Yeah.
Okay.
The rougher the surface is, the higher the chances are that energy get lost.
When it would have been reflected in a perfect model.
Yeah, figure 12
Yeah.
shows that quite well.
Yeah. But look at figure 15 and 16 are a visual demonstration of what that consequence is, where they have a background and a material that it's like a mirror, and then the sphere that's a perfect mirror. And it should, bounce back the same amount that comes in. Is it a mirror? Perfectly.
That furnace test.
Yeah. And as on figure 15, it's getting darker because that's the light being lost to scattering a scattered light that would have been reflected had the BRDF accounted for it.
Basically the bad model, or not bad, just insufficient.
Yeah.
Okay. Yes, stochastic evaluation. That's probably not fast enough.
Never is.
Uh,
It feels like.
The idea is to add an energy compensation term. So basically cheating, but yeah.
So maybe it's not the G term that causes it. Maybe it's more of a like everything together. Because
I think it's the G term cause it, but they just add another energy compensation term to compensate the effect. Should we get back the
glossary? Yeah, I was just thinking that.
you see the two tab together?
No, just the one.
Just seeing the one on yours.
Okay, let me share it again. Share the whole screen. Can you see it now?
Yes.
Yep.
So it's about instant light and the view unit. Where is the roughness in here?
Alpha? Or you're talking about the equation. Sorry.
Yeah.
I don't think they take it into account.
Yeah, I think they're doing it in terms of energy here. Maybe I'm not sure. No, it's directional albedo.
JB, do you have your microphone near like a fan or something?
Oh yeah, let me.
Yeah.
Thank you.
Is that better?
Average.
Yes, definitely.
Yeah. I can still hear something, but it's better.
Yeah.
Yeah, there's something running outside. I'm not sure exactly what. I can turn down my mic a little bit.
So E is the directional albedo. I wonder why they set F0 to 1.
Is that saying that all the light is or is F0?
That's
Reflectance.
Oh, at normal. So it's saying it's perfect at F0 where all the light is returned.
Yeah.
Which
why.
That's the least worst case, judging by figure 12, in terms of the amount of light that's being lost to lost reflections, lost scatter. So that's probably why. I could be wrong though.
Both T term E and E average. E average is cosine weighted average. Can be pre-computed and stored in a lookup table. That's interesting.
Oh yeah, because E is over the whole hemisphere, right? So
Yeah.
or
and
sphere actually.
also, yeah, we know the BRDF. So and then we can just calculate it and store a lookup table. And
So would
that's
that be a
interesting.
3D lookup table, I guess? That seems quite expensive, if so.
Yeah, it depends on L. I don't know.
They claim in after 31 further down that we can implement specular energy compensation at a negligible cost if we store R in the DFG lookup table presented in section 5.3. That implies.
Okay, so
what's the DFG?
we can wait. Yeah, we can wait until when we talk about the 5.3 to know what is going on here. But if this can be stored in a lookup table, then I don't think it's 3D.
Yeah, I have a suspicion that this is a constant, not a constant, but it's irrespective of. It can be multiplied by the roughness to get the compensation required based off the angle.
Yeah. The Fresnel average term can be also greatly simplified because we use Schlick approximation. Probably this is just a bunch of calculus to derive from here to
Yeah.
here. The new lobe is combined with original single scattering lobe, previous noted FR. I don't understand that.
I think it's saying that you get the original single scattering computation amount, and then you add in the compensation to it to get the total reflectance. So
Yeah, I think
FMS is
Oh, I
the
see, I see. Yeah.
it's the multi-scattering term is the compensation. Yeah.
is that 1 plus 20 times FO over 21? Is that the Schlick approximation? It looks so
The Schlick
tacky.
approximation is like to the fifth. So when doing some weird calculus stuff, we get those numbers, right?
And then the after equation 28, it says, oh, you can just simplify it to F0. I'm like, great. So they take that, even the 1 plus 20 FO over 21, and just turn it into F of O, or F of 0.
Yeah.
I think that period's supposed to be a comma also. Maybe.
Oh yeah, didn't they earlier set F0 to 1, which would be, or is this
Yeah,
that
F0
only
is-
for the E part?
Or
Yeah, I think it's only for the E.
Okay.
okay, and then we're further simplifying that back down to F0 equals 1. Is it? Or no, it's just F0. Oh, okay, it's not that.
Yeah, it doesn't go that far.
Yeah.
Right.
Can not only be pre-controlled but also shared with image-based light in pre-integration.
So wait, wasn't what is the F term in the E function? Like the E, like isn't that F the BRDF?
E is the directional albedo of the specular BRDF. So it's the
In the table, they just say it's generally the BRDF, the F term.
So
Yeah.
that F term in E eval is going to be basically the single scattered
yes.
version. Okay, so then the multiple scattered one. So the final one has the single scattered one quite a few times then.
Well, I
Yeah.
think 30 is pretty much the final one.
Oh yeah, okay.
So we have the single scattered plus the single scattered times the compensation factor, which is 1 over the reflectance minus 1. So it's a does it dampen it? And it's then times F0, which I'm not sure what that means here.
Wait, what's R? Oh,
It's
sorry,
well-
right.
R is 1 over E. Is it 1 over E? Oh,
Wait, what is her?
R is that
Yes.
integral in 31.
Oh, Okay, it's okay.
Yeah.
But wait, what are D and V? Yeah, wait, what are D and V?
Do
I think
we,
they pull those out of somewhere.
I think
D is the distribution and V is the visibility range. It's the two terms we talked about earlier in the
yeah, from last week.
Is
yeah.
it?
Wait, really?
The
Yeah,
D
it's
definitely.
this.
I have G for visibility, which is highly confusing. But V would make sense.
V is kind of G
Oh, right.
and
Yeah.
divided by something. And then
Oh, and D is just the GGX distribution. Okay.
yeah.
Okay. I just forgot what it was.
So it makes sense that the R term here is proportional or is relative to how much scattering and diffusion there is going on to the surface, because it's trying to compensate for the fact that the surface blocks some light that should be, or we're not catching some light that would have been reflected. So the more bumpy and lumpy the surface is, the less lost light we have, or rather there's more light that is being absorbed in total, and some of it would have been reflected. So we have to, I'm just trying to reason it through my own voice.
Okay. So later we will look back and talk about this lookup table.
Yeah, that'll be fun.
Parameterizations, so 4.8. It's numerous. Disney's model's numerous parameters make it impractical for real time. I think in real time, usually it's just metallic and roughness.
Yeah.
And emission.
Emission isn't even like originating in the PBR space. It's kind of been emission has been a texture. Yeah. Similarly with ambient occlusion being just kind of a hacky, hey, well, it's hard to actually compute local lighting effect, so we'll just pre-compute it and put it in a texture.
Yeah, base color.
So it's interesting that they separate metallic surface into dielectrics or conductors. And
it's often used in, because if you have 0.5, it's really weird. It's some kind of weird semiconductors that usually you just can't see things like that in real life, and it will look really weird.
Yeah.
Optical semiconductor.
Roughness, we already talked about that. Reflectance. Fresnel reflectance at normal instance for the electric surfaces. Okay.
That's just the F0 term, right?
No, it's going toward, it's not at normal incidence, it's at 90 degrees. Or
wait,
so it's the F90 turn, not the F0 turn.
Wasn't F90 like a tangent?
F90 is the grazing angle.
Yeah.
Yeah.
And we usually use 1 for F90. So Though maybe later they will talk about like better treatment for what F90 should be. But now it's just one. I think they will later they will talk about what's the relationship between this reflectance and F0.
Yeah.
Emissive. Also used in HDR pipeline with a pruning path. This ambient occlusion, it will be discussed later. Metallic roughness and reflectance. Yeah, so this is the electric, this is metal. Roughness change. Is also roughness change.
The bottom, I guess, the Fresnel term remains relatively similar across the range of reflectance.
The third row is metallic roughness.
Really,
Yeah. Type and range.
I mean, basically, what are vectors and what are scalars? Plus a little bit of exposure compensation for the emission.
Yeah, what is that?
So it's, yeah, I think it's going to be down to your implementation, like how you compensate for your emissive, if you want it.
Is that going to be like a fourth term or?
Oh, because emissive can be, yeah, you multiply all the linear RGB by the exposure compensation, I guess.
Okay, so that's going to be a vec4 basically, is what you're saying.
You could be,
Or
you could back it up.
U8 vec3 plus a float, I guess.
I thought, okay, I don't know.
Could be expressed in SDR-RGB space and convert to linear space before send off to the shader. Yeah, I guess so.
Okay.
Color temperature and intensity, yeah. Remapping. So it's basically talking about how to make those parameters more intuitive.
Yeah.
Base color.
So this looks to be saying that dielectrics, their specular reflection is achromatic, meaning it just has it doesn't have a color to it, it's just a brightness. But their base color is still the diffuse color, whereas conductors do have their base color in their specular highlights and don't have a diffuse component. So
That's how they get their color. That's why like gold is yellow. You know, it reflects like the yellow sort of colors.
yeah.
It doesn't have a diffuse color, so
Yeah, so the more metallic something is, the more the diffuse color lacks the base color in it. To the point of when you're 100% metallic, you have no diffuse color. It's all specular.
Yeah, in
It's
real
like,
life, it's only one or the other. That's the
like if it's in like a room with no direct light, then like I don't know, wouldn't you not see color on it? Trying to like wrap my head around that.
on metal. It'd
Yeah.
reflect indirect light.
But like,
And-
but
and
only
some
at
and some of it
specular
would still be
angles, right?
scattered due to the roughness of the material.
Yeah.
So what if you had like a completely dark room and like a extremely focused spotlight?
Well, if you scroll up, there was figure 14 has. I mean, that's basically what it looked like, I guess.
Where?
We're basically all black except on this tiny specular lobe.
Right. Interesting. It's hard to picture that in real life, but I guess that makes sense.
That'd be
Actually,
a really weird scenario because the light would bounce off the metal thing and then it would like hit the room and then bounce off, the walls in the room
yeah.
and then back onto the sphere.
this actually, I know of a video that's kind of like that. The guy painted a room with Muso black, and anything that isn't in direct light can't be seen, pretty much. Just because there is no backlighting or reflected lighting.
Okay. Yeah, I would love to see then what like a pure metal thing had a light shine on it in that room. Yeah, I guess the rest of it would be black.
I mean, if it's a shiny object, it would be pretty much only the highlight would be seen. But if it's a very
Yeah.
rough object, you'd get that normal, metallic sheen on it, like the third row on the very right of the four rows of four rows of spheres.
Yeah.
That's what it would kind of look like, because it's just scattering it everywhere. And all of those just have a single light source, although they do have IBL, I guess, or some sort of global lighting thingy.
Right. Yeah.
Because
It's
because you can see the background in the
Yeah.
metal ones.
it's just never a scenario we encounter in our daily lives, so it's
Yeah.
kind of hard to picture.
Yeah, I guess it makes sense. But weird.
Yeah. So
Reflectance remapping.
Oh, so they're having to make the reflectance 0 to 256 value into a more physical quantity to match how the different materials in the world, like water is 2% versus diamond being 16%.
Right. It is
Which-
just 0 to 1 though, I think, right? Reflectance.
Yeah, but that's why they want it to be useful.
Mhm.
There's a whole bunch of index of refractions for materials that people don't think about refracting light.
That is interesting.
Yeah, hair.
Teeth.
Index of refraction can derive Fresnel reflectance. Okay. That makes sense. What is IOR? Oh, index of
refraction.
refractions.
I wonder where. Do any of you know where the like -1 +1 squared comes from?
That's the how IOR is calculated, or what? I'm now confusing myself.
I'm not sure where that's coming from.
Yeah, maybe
I
it's
feel
just
like that's
trust us.
how refraction indexes are, but then it's squared and it's +1 -1.
It just be like that.
Yeah, I guess so.
I guess because we never talked about how the Fresnel and the index of refraction are related to each other. So it's just look kind of like magic.
Seems to be a little bit of a theme in this publication.
I'm seeing n1 minus n2 over n1 plus n2. And I think for, can I get how do I link to this? Open image in new tab. No, that's just LaTeX. Thanks.
I think I see the one you're talking about on Wikipedia under reflectivity.
Yeah, and what's confusing us is that one, that's the Ior of Air. So we're missing, we're assuming all of these are relative to air, because Ior is always two different media, and for what we care about, it's air and something else that isn't air. So that one is just kind of there, and it looks suspicious, but it's an already filled in constant variable.
Cool.
So
I guess that means if you're doing underwater rendering or something, you're gonna have to change your equations a little.
Yeah.
Well, it's actually I've done a little bit with that. It's actually you can use negative values for, or not. I forget exactly how it works. It was either negative or it was less than 1. But
Less than 1.
You can use the same.
Yeah, because water to air, or the air-water Ior is 1.33, but I bet that if you're underwater, you'd basically, everything would go from like 1.33 to like 0.8 or something.
Yeah.
What's the linear value?
That's the grayscale color image thing. So if the IOR is 1.33, you'd put a 0.35 on the grayscale input image on the reflectance map.
Oh, and it gets remapped.
Yeah.
Okay.
So yeah, this is, it's all about, hey, we want to store these in a human-friendly, or not a human-friendly, but a map of color values, but we need to map this to a useful number quantitatively useful number, which is what the IOR is. Because you can see the linear value goes from 0 to 1. Nothing is greater than 1 and nothing is less than 0.
Yeah.
And most of it's from 0.5 to 0.6, 0.4 to 0.6.
I guess they still want to leave it open to have some unrealistic materials, but
yeah, that's what I said last time. They said like all parameters you can use arbitrary number and all will be realistic. It's definitely not the case.
yeah. Oh, actually, it looks like though they. Okay, there is a 1.0 in there for a diamond. Okay, so they don't actually let you do too crazy.
Hence the mapping.
Yeah. But they still let you go below water, which seems to be often the lowest.
Yeah.
I mean, the 0 would be air effectively. So
but they cap it at, what was it, like 0.016 or 0.16? Or no, never mind. Okay, yeah, so you can still just get to 0.
I wonder what. I don't think I can Google materials with low index of refraction and get anything useful.
Probably liquids. If I had to guess.
I feel like water's probably got to be one of the lowest, though, right? Liquids. I feel like most other liquids aren't really as clear.
I mean,
Oh, I guess higher index of refraction. Wait, so the air divided by? Yeah, I think it's air divided by the other things index of refraction, because there's no way light goes faster in like diamonds and like random solid materials than it does air. Right, because
Yeah.
water's index of refraction is 1.33,
I can't.
which
click
is
on-
faster than like diamond, I guess, which is like 2.4, 2.3 something.
Okay, so I guess vacuum is 1 by definition, and then everything else
Yeah.
is higher from there.
And air is so close to it just because it's so sparse compared to everything else that's a
Yeah.
solid at room temperature,
Yeah,
atmospheric
we
pressure.
basically treat air as vacuum, except when we atmosphere scattering, right?
Oh yeah, because we're all
Helium has a lower index of refraction than air, I think.
helium.
I think so.
I mean that tracks.
Yeah.
But it's probably not less than 1.
No, it's not.
Yeah.
Uh,
I thought you
that's
said
why
less than 1 at
vacuum.
first.
You can't be less than 1.
you go faster than the speed of causality and you
Yeah.
destroy the universe.
Yeah. The light would destroy the universe before the universe even knew it.
Okay, so you would see numbers less than 1 if you were in water and looking at air, kind of a thing, yeah, because as a ratio kind of thing.
Oh yeah,
from
it
your
does go below water. If you're going from a slow surface, or sorry, slow material like water to air, it'd
yeah.
go below 1.
Makes sense.
Or it'd go below 1 after you, when you do the math.
Yeah.
I have some renders like that there. A little bit. They look funky.
F90 is, yeah, they just use 1. And this is Fresnel again. I guess Fresnel does make a difference to make this image looks real, and also image-based lighting, I guess. Conductors.
Okay, and with the Fresnel term, you're saying more of the scene color at those grazing angles.
So what is list 12?
Mm. It's just that little piece of code, I guess.
I realized that after I sent it.
Okay, I guess it's basically a lerp between 2 terms. And if we just use metallic of 0 or 1, then we basically get other either this or that.
Right, yeah. Yes, metallic 0, then you remove the base color.
Perceptual roughness, which is square root of the real roughness. Okay. Yeah, this kind of looks better compared to this.
Well, it's really not what looks better. It's just what's more useful. Going between. It shows a more linear relationship between it. When in
Yeah.
reality, it's not a linear relationship.
It's just perceptually shows kind of like this one for the right hand side, you cannot tell the difference.
Yeah.
Yeah, you lose that highlight way too fast.
Yeah.
Yeah.
Like is that 10 gradations, 11 11 spheres across?
Yeah.
So yeah, the bottom one, the rightmost 5 of them are pretty much identical. It's a little bit of difference, but there's almost nothing. And like it goes from I'm reflective to I'm rough in about 2 spheres, which is not very fun to use when you're trying to change the brightness of the thing, and you have to move the mouse a pixel only to get the exact value you want on the slider.
Yeah, I've seen the same type of thing with alpha. Sometimes when you do alpha blending, sometimes you want to raise that to a power to give yourself more usable range like this. Because yeah, it goes from transparent to opaque in like the first 16 of 255.
Yeah.
Like,
Oh. That's interesting. Because they're squaring the roughness value, they occasionally get times where they're actually squaring the square, meaning get to the 4th power, and that results in divides by 0 on half floats if you're not careful. And they clamp it to 0.01 or thereabouts to prevent that. The roughness can also not be set to 0 to avoid obvious divisions by 0. Are they saying that you can't? You limit the artist's ability to write a roughness value of 0? You say, okay, it actually has to be 0.01.
they must have a different material for perfect reflectors.
Possibly. Yeah, and I don't think many surfaces are like that. Even mirrors are not perfectly reflective. Is this reflective? No, that's roughness. That's different.
Is it?
It's the same, right, in this case?
Not reflectance and roughness are not the same, from my understanding.
But like when it comes to being a perfect mirror or not, right?
Well, I'm just imagining the material could be polished to a perfectly flat plane and still be hella diffuse.
Okay.
Whereas you can take a like it's like tin foil. It's very, very shiny, but if you crumple it up, I mean, you imagine you could crumple it up on the microscopic scale. You'd get a very different look than if you had a very, very diffuse, perfectly flat surface.
Isn't that just increasing the roughness, though?
I mean, well, one of them is, yes.
So I feel like I don't know. Like, is it the case that like, so like roughness in this case means basically how different the little microfacets are. So I don't know if you have a very diffuse material with low roughness.
I
Isn't that-
imagine yes. I like
I think it's no.
So I feel like the roughness is kind of what tells you how much diffuse there is, almost, right?
Yeah.
well that's one of the original, like the Phong shading model back in the day just had a single diffuse term and it lumped those two concepts together. But what we see here is that the reflectance of a surface and the roughness are separable terms, and you can get different effects by having different roughness and reflectance.
But the reflectance is, yeah.
Of course, there's also the metallic, the dielectric divide.
Yeah.
So the reflectance is basically just F0. So it's how much is reflected at the normal.
Yeah. Normal incidence.
Okay.
At least that's my understanding of the gist of it all.
Yeah, that makes sense, but I'm trying to like reconcile that with
Right.
the
I'm kind of
microfacet
with you on
stuff.
the. I can say things and not actually believe what I'm saying.
Hmm.
Blending and layering.
It's combining materials.
Interpolating. Using simple mask.
Is it basically saying that you could have two or three materials apply to an object, and you have a parameter that controls how much of each material to sample? So, or is it saying that you just have a single texture for the entire object, and the interpolation between areas of varying properties is continuous and smooth and nice looking?
So the blending and layering of materials is effectively an interpolation of the various parameters of the material model.
Yeah.
Okay, so it's probably
Yeah, I think you could bake in like the interpolated values into the texture, like if you want to just apply it.
Oh,
But then you cannot do it dynamically, right? If you bake into texture.
yeah, but
Sure.
if you imagine texture painting, you have like this trash bin here. You're in your texture painting program, and you say, well, it has like 4 different areas of different material properties, and you're painting the weights between all of them. Then it gets baked down into the final texture.
Yeah, I guess so. We can have an asset pipeline to generate those textures.
Right, that's what I meant.
Yeah, it's how I interpret that.
The interpolation though is just for blending, right? I can't see how that works for layering though. Because like
It's also for layering.
then they have a whole section for their clear coat model, which I feel like is
I
not
think
just
that's
kind of
completely.
layering.
I think
Oh.
that's different from like blending between like metal and wood. I think that's a different concept.
So what does layering mean here? Like as opposed to blending?
Oh, actually, that's a good question.
Because I think you're right though. Like I think they are just using layering here as well, but I'm just not sure.
Yeah,
what it
they
means.
said blending and layering of materials is effectively an interpolation of various parameters of the material model.
So they're just using
So
it as a synonym.
maybe they're just assuming that the layers are thin enough that we could kind of blend.
Okay.
With the red sphere or the chrome to red sphere here, it looks like you stretched plastic really thin over it, maybe for something.
So I think the description, okay, the description further below, I think like about the clear coat model makes this make more sense, because it's describing that you'd have commonly a single layer above it that it's the clear coat, wood with lacquer, car metal with paint on it, and other behaviors like that. And so having the clear coat layer is a separately defined thing. And I think that's what they're referring to, but maybe I'm reading too much into it.
I guess we need to read later to understand.
Yeah.
Yeah, base color, metallic, roughness, reflectance.
Interesting how for metals and non-metals, they still just have a single base color. And it's just kind of like behind the scenes that it's
Right above
behaves
figure
differently.
22, I think it explains, at least answered your question about blending and layering. It just says that the blending and layering of materials is effectively an interpolation of various parameters of the material model. And then it makes little physical sense, but it looks plausible enough.
Okay, so not like a real physical layer.
Yeah, it's just if you're like, I guess for artist painting or whatever, like blending between two materials that are adjacent. I don't think you would normally have like a large intermediate blended material. It'd just be like where metal and wood meet on
Right.
something.
Okay, that makes
Using
a lot of
clear
sense.
coat as a special case.
Yeah, that area where the two different materials meet, that makes a lot of sense for where this applies.
Because yeah, they're saying that blended materials are not physically plausible a lot of the time.
Oh yeah. What, you can't evenly mix wood and metal in equal parts at a constant constantly varying distribution from 0 to 1 and 1 to 0.
Oh, wait, so looking at that chart again, they say reflectance, they describe it as specular intensity for non-metals. So I guess that is kind of different than diffuse stuff. It's basically just like how much light is lost if for the pure specular, but maybe doesn't necessarily, like the lost light doesn't necessarily come back out as diffuse light. It's just lost. So I feel like you could have a really low reflectance, but that doesn't imply that it's diffuse. It just means that you don't get as much light out of it.
Yeah,
I'm not sure.
and they say it's no real wood material is below water's reflectance.
My read is specular intensity, meaning how strong is how concentrated is the specular lobe, basically how scattered is the specular highlights, where one is super highlighting like gemstones, whereas at 0.5 it's kind of half and half.
Yeah, okay, that makes more sense. But yeah, I guess it's still doesn't have anything to do with the diffuse stuff.
Or the roughness. I love how there's the roughness metalness model and like the reflectance glossiness, and they kind of mean the same thing, but they don't. And then, we have two places in here where it says this is sometimes called glossiness, the clear coat roughness as well, which is not confusing at all.
Oh, I guess that is the same roughness parameter, but it's just for the separate layer.
is this? She's a witch.
Well, it floats, so therefore she's a witch.
Gotta burn it to find out.
That was worth saying.
Do you
Okay, I
wanna-
think we're done. And
Yeah.
yeah, we can stop it here.
Yeah,
It's an hour now.
yeah, we got clear coats and thin layers ahead of us, so that'll be good for a single.